Okay, we talked in last lecture a little bit about how the conjugation of a carbonyl group will reduce the frequency in an infrared spectrum, and I'm going to go a little bit more into the frequency of a carbonyl because it could be affected by a number of things. So normally we see a carbonyl stretch at about 1715 wave numbers, but it can vary depending on inductive effects in the molecule, any resonance effects that we see, and also where the carbonyls in a ring, how big the ring is. So the first factor is inductive effect. So we have a carbonyl compound like so, where we've got a substituent called X, and depending on what X is will depend on the frequency of absorption, so the frequency of the infrared stretch. Now if X is a hydrogen, in which case we would have an aldehyde, we would see a stretch of between 1720 and 1700 wave numbers. Now that increases if X is now a methoxy group, so we have an ester compound, and it increases further if X is now a chlorine, so we would see that would be for an acid chloride, so our stretch would be even higher at about 1815 to about 1790 wave numbers. So what we're seeing is as the electronegativity of X increases, the wave number of the carbonyl stretch increases as well. What about resonance? Well, in resonance we see conjugation. That's what resonance is. And if we look here, we've got a 6-membered ring with a carbonyl bond. We'd see that carbonyl stretch around 1715 wave numbers in our infrared spectrum. But if we actually now looked at a 6-membered ring with a alkene bond within it to enable resonance with the carbonyl group, that frequency reduces to 1680, and as I showed in one of the previous examples in lecture 2, that's because we've got resonance which results in a single carbon-oxygen bond being formed. So by this resonance we're reducing the double bond character of the carbonyl, and therefore the frequency is decreasing. What also affects carbonyl frequency is ring size. So as our ring size decreases, we see an increase in the strain of the ring, and we look a bit more at ring strain in second year, and that results in an increase in wave number, which corresponds to an increase in the frequency of infrared radiation being absorbed by the molecule. So in a 6-membered ring we see a carbonyl stretch about 1715 wave numbers, but if we reduce the size of the ring, that wave number increases by about 30 wave numbers. So that's a few things which affect this carbonyl frequency, but there's a few other things to consider with carbonyl compounds, because we have an awful lot of functional groups which contain a carbonyl bond. So the carbonyl stretching frequency can be very similar for different functional groups. And so we need to use other signals in our spectrum to assist with determining what functional groups we have. So let's look firstly at an ester. We have a carbonyl bond, so that will give our carbonyl stretch, but we also have a carbon-oxygen single bond here, so we would also see a CO stretch around, say, 1200 wave numbers in our infrared spectrum. If we had a carboxylic acid, we would not only see the carbonyl stretch, we would also see the carbon-oxygen single bond stretch, similar to the ester, but we would also see a big wide stretch between 2500 and 3500 wave numbers that corresponds to the stretching of the oxygen-hydrogen bond, if it's hydrogen bonded, and a slightly smaller range if we don't see any hydrogen bonding, but we will still see that OH stretch. So in an aldehyde, as well as the carbonyl stretch, we also see stretches corresponding to this carbon-hydrogen bond, and we'd see 2 bands, so 2 peaks, between about 2850 and 2700 wave numbers. So we've got a lot of other functional groups to consider as well. What about amines? So in amines, we get nitrogen-hydrogen bending around 1600 wave numbers. We also see stretching of the nitrogen-hydrogen bond above 3000 wave numbers. And what's important to note is that in this range, if we have a primary amine, we tend to see 2 peaks, and in a secondary amine, we tend to see 1 peak or one spike in our spectrum. What about triple bonds? So we touched on this in the earlier lectures. We would see a stretch of about 2200 wave numbers if we've got an alkyne. So that would be our carbon-carbon triple bond stretch. And we'd also see a CH stretch accompanying that around 3300 wave numbers. If we had a nitrile, again, same frequency, about 2200 wave numbers would correspond to our carbon-nitrogen stretch. So let's look at a few more examples now. So here we have benzoic acid, and it's this structure here. It's a benzene ring with a carboxylic acid on it, and this spectrum's done in newjoule mole, so we have to take into account those peaks I was talking about in earlier lectures, about what peaks does our newjoule mole give, and make sure that we don't consider them as being part of our molecule. So we've got a couple of peaks here which are part of newjoule, and these peaks here are coming from our newjoule mole as well. So let's look at the other peaks in the spectrum. Well, we've got this very broad peak here, which corresponds to our OH group of the carboxylic acid being hydrogen bonded, so giving this really broad signal. We've also got some aromatic CH stretching corresponding to this peak here, which is above 3000 wave numbers. And if we look further down the spectrum, we've got a conjugated carbonyl group. I've drawn the resonance form down here. So slightly lower wave number than for a normal carbonyl because it's conjugated. And then around 1600 wave numbers, we have these aromatic ring vibrations corresponding to carbon-carbon double bond stretching. And around 1300 wave numbers, we've got the peak that corresponds to our carbon-oxygen stretch. Now, it might look a bit overwhelming to see so many peaks here and not really knowing which one to pick out. Normally, the most significant peaks are labelled with an exact wave number. And as you look at more infrared spectra, you'll start to be able to pick out the key peaks, such as CH stretching, carbon oxygen double bonds and carbon oxygen single bonds, and these aromatic ring vibrations. So it's really just a case of looking at more and more spectra to be able to spot the key peaks. Let's now look at an ester that's also aromatic and see what peaks we're seeing in that infrared spectrum. So we've got methyl benzoate here. It's run as a liquid film, which just means it's neat. We're just putting the liquid on our in our infrared spectrometer, so we don't need to worry about newjoule peaks in this instance. So above 3000, we've got aromatic carbon-hydrogen stretching, and below 3000, we have aliphatic carbon-hydrogen stretching. So these peaks here, because we've got this aliphatic methyl group. We've also got to consider that we've got an ester here, so we've got the oxygen electron withdrawing group, drawing electrons away from the carbonyl. So we've got this slight increase in shift of our carbonyl peak, a slightly higher wave number than we'd expect for other carbonyls. Around 1490 to 1600 wave numbers, we've got these aromatic ring vibrations, carbon-carbon double bonds, and we've also got this carbon-oxygen single bond stretch, about 1200 wave numbers, which is corresponding to this, this carbon-oxygen single bond in our ester group. So what about an aromatic aldehyde now? So another carbonyl compound, but with a different substituent to a carboxylic acid or an ester. Just got a hydrogen here. So above 3000 we have these carbon-hydrogen stretches, they're aromatic. Below 3000, not only have we got CH stretches for aliphatic CHs, which are likely to be buried under here, we can also see clearly two peaks which correspond to the aldehyde doublet, is what we call it, these two bands around 2700 to 2800 wave numbers. Because this carbon-oxygen double bond is conjugated, our stretch for that bond is about 1700 wave numbers, and we've also got our carbon double bond aromatic stretches around 1600 wave numbers here. Also, just so you can see, but this is just merely for information, we've got a few peaks down here which correspond to the phenyl ring being mono-substituted. So when we get into a bit more advanced infrared spectroscopy, we can consider how our peaks in the fingerprint region correspond to the substitution of the phenyl ring. So if we leave carbonyl compounds for the time being and look at something different, so this is an alcohol, it's benzyl alcohol. We've got not only a phenyl ring, we've got this OH group. We can see that we have above 3000 here, we've got really quite broad peak, and that corresponds to our hydroxyl group. Hydrogen bonding in this fashion here, so to form dimers or trimers, so that's where 2 or 3 molecules bond together, but not via covalent bonds but via dative bonding and hydrogen bonding. So we've also got aliphatic carbon-hydrogen stretches below 3000 wave numbers, and we've got this carbon-carbon double bond stretch peaks around here as well, which correspond to the phenyl ring. So what about if we look at compounds with nitrogen in them? Okay, now let's look at some amines. So here we have cyclohexylamine. It's a liquid film, so we don't need to worry about subtracting any peaks from nu-joule mole. And we've got some interesting peaks here. So the first thing is it's a 6-membered ring. We've got 6 carbon atoms on this ring, and there's going to be CH stretches. So aliphatic CH stretches are going to come below 3000 wave numbers, as so. And then we've got these peaks here which correspond to the NH stretches. It's a primary amine, so we've got 2 sharp peaks. We've got a symmetric stretch and an asymmetric stretch at 3300 and 3275 wave numbers. What we also see here is an NH bend around 1600 wave numbers. What happens if this 6-membered ring is not an aliphatic ring but an aromatic ring? We see a bit of a difference in the spectrum. So we've got aromatic CH stretches here around 3000 wave numbers. We've still got these 2 sharp peaks corresponding to NH stretches in a primary amine around 3300, 3400 wave numbers, and this group of peaks here corresponds to both NH bend and aromatic carbon-carbon double bond stretches. So what about if we do a spectrum of an amine in nu-joule mole? This is just to see how the spectrum might change. We've got a di-substituted phenyl ring here, so we've still got a primary amine in there, giving our 2 stretches around 3300, 3400 wave numbers. Because we've looked at a nu-joule mole spectrum already, spectrum 0, we know that these peaks here and this peak here is due to nu-joule. So the other peaks we just need to assign are these around 1600 and 1500 wave numbers, which correspond to aromatic carbon-carbon double bond stretches. So let's now look at secondary amine. So we were looking at spectrum 12, which was corresponding to a primary amine, and now we've got an extra group on the nitrogen that's not hydrogen. We've got this ethyl group. So we've now only got one nitrogen-hydrogen stretch at 3,400 wave numbers. We've still got carbon-hydrogen stretches, which are both aliphatic and aromatic because they appear above and below 3,000 wave numbers. And we've got an NH bend to consider at around 1,600, plus these carbon-carbon double bond stretches around 1,500 and 1,400 wave numbers. What about if we now look at some triple bonds? So we've got ethinyl benzene, also called phenyl acetylene, and we have a phenyl ring with a triple bond as a substituent, this carbon-carbon triple bond. So not only do we see aromatic carbon-hydrogen stretches here, we also need to look out for the effect that the alkyne has on our infrared spectrum. We have a carbon-hydrogen stretch corresponding to the carbon-hydrogen in the alkyne, around 3,300 wave numbers. And then we have our carbon-carbon triple bond stretch from the alkyne, about 2,100 wave numbers. And we've also got some peaks here. Really the strongest is just this one, about 1,500 wave numbers, that corresponds to our carbon-carbon double bond stretches in our phenyl ring. So finally, before we look at how we apply infrared spectroscopy to monitoring reactions, let's just look at another triple bond example. So this is a nitrile. The nitrile is conjugated as so. We can draw resonance forms. So our spectrum here, the carbon-nitrogen stretches a bit of a lower wave number than we'd normally expect, and our aromatic skeletal vibrations again appear about 1450 to 1500 wave numbers. So that ends lecture 3, and next lecture we'll be looking at how we follow reactions using infrared spectroscopy.